Asteroids and Comets, Cosmic Time Bombs Waiting to Strike. Part 1. The Difference Between Asteroids and Comets. The solar system is a vast cosmic shooting gallery, teeming with smaller celestial bodies that often get lumped together, but asteroids and comets are distinct entities with different origins and compositions. Asteroids are predominantly rocky or metallic remnants from the early solar system, akin to planetary building blocks that never quite coalesced into a full-fledged planet. They mostly reside in the inner solar system, particularly in the asteroid belt between Mars and Jupiter. Their surfaces are generally solid and airless, reflecting sunlight with varying degrees of reflectivity based on their mineral content. Comets, on the other hand, are often described as dirty snowballs or icy dirt balls. They are composed of ice, dust, and rocky material, largely unchanged since the solar system's formation. These icy wanderers originate primarily from the distant frigid reaches of the solar system, specifically the Kuiper belt and the Oort cloud, far beyond the orbit of Neptune. When a comet's orbit brings it closer to the Sun, its volatile ices begin to sublimate, turning directly from solid to gas, creating a glowing coma and a characteristic tail that can stretch for millions of kilometers. This process makes comets visually spectacular, but also rapidly depletes their icy reserves over time. The key differentiator lies in their fundamental makeup and behavior when encountering solar radiation. Asteroids remain largely inert, their physical form unchanging unless subjected to a collision. Comets, however, are dynamic objects, their appearance dramatically altered as they approach the Sun. The tail, a defining feature of a comet, is formed by solar wind and radiation pressure pushing dust and gas away from the nucleus, always pointing away from the Sun, regardless of the comet's direction of travel. This distinction is crucial for understanding their potential impact hazards and their roles in delivering materials across the solar system. Their differing compositions also hint at their birthplaces. Asteroids, rich in silicates and metals, formed in the warmer inner regions where volatile ices could not survive. Comets, conversely, formed in the colder outer regions where water ice, methane ice, and ammonia ice were stable. This chemical and geographical separation provides astronomers with valuable clues about the conditions and processes that shaped our solar system billions of years ago. Studying these ancient relics offers a direct window into the primordial cloud of gas and dust from which our Sun and planets emerged, preserving a record of the early solar nebula. Understanding these differences is paramount for planetary defense strategies. Detecting an incoming asteroid, a solid chunk of rock, requires different observational techniques and mitigation strategies compared to tracking a comet, which might appear suddenly from the outer reaches of the solar system and develop a large, diffuse coma. The density, trajectory, and potential fragmentation patterns of these two types of objects would also vary significantly upon atmospheric entry, impacting the scale and nature of any terrestrial event. Thus, distinguishing between these cosmic wanderers is not merely an academic exercise, but a practical necessity for safeguarding our planet. Part 2. The Asteroid Belt Myths versus Reality. The asteroid belt, often depicted in science fiction as a densely packed minefield of constantly colliding rocks, is a far more spacious and surprisingly empty region of our solar system. The reality is that if one were to fly a spacecraft through the main asteroid belt, the chances of encountering a close approach, or even seeing an asteroid without specialized instruments, would be incredibly slim. The sheer volume of space within the belt means that even with millions of known asteroids, the average distance between them is vast, typically hundreds of thousands to millions of kilometers, equivalent to multiple times the Earth-Moon distance. This misconception of a crowded belt likely stems from dramatic cinematic portrayals, where spacecraft must constantly dodge and weave through a chaotic swarm. While collisions do occur, they are rare events on human timescales, often involving small fragments or dust rather than spectacular impacts. These infrequent collisions are, however, a crucial mechanism for generating meteoroids that can eventually fall to Earth and for reshaping the orbits of existing asteroids. The debris from such impacts can create new families of asteroids with similar orbital characteristics, providing astronomers with insights into the belt's dynamic history. The asteroid belt is primarily located between the orbits of Mars and Jupiter, roughly 2.2 to 3.2 astronomical units from the Sun. It contains millions of objects larger than 1 kilometer and many more smaller ones, but their combined mass is still less than that of Earth's moon, representing only about 4% of the moon's mass. The largest object in the belt is Ceres, a dwarf planet approximately 940 kilometers in diameter, followed by Vesta, Pallas, and Hygeia, all significant bodies in their own right. These larger asteroids exhibit characteristics more akin to miniature planets, with differentiated interiors and even signs of past geological activity. The prevailing scientific theory suggests that the asteroid belt represents the remnants of a protoplanetary disk that never formed a full-fledged planet due to the gravitational perturbations from nearby Jupiter. Jupiter's immense gravity prevented the smaller planetesimals in this region from accreting into a single large body, instead stirring them up and keeping them in distinct, somewhat chaotic orbits. This gravitational influence also explains the Kirkwood gaps within the belt, regions where asteroids are scarce due to resonant orbital periods with Jupiter, causing them to be kicked out of those particular orbits over long periods. Despite its relative emptiness, the asteroid belt is a treasure trove of information about the early solar system. Each asteroid is a time capsule, preserving the conditions and materials present during the planetary formation epoch. Studying their compositions provides clues about the distribution of elements and compounds in the primordial nebula, offering insights into the building blocks of planets, including Earth. It is a dynamic laboratory where scientists can observe the ongoing processes of accretion, fragmentation, and gravitational interactions that continue to shape our cosmic neighborhood, far removed from the dramatic but inaccurate imagery of popular culture. Part 3. Famous Impacts in Earth's History. Earth bears numerous scars from past cosmic collisions, remnants of a violent history stretching back billions of years. While many early impacts have been erased by geological processes like erosion and plate tectonics, some of the more recent and significant events have left indelible marks on our planet's surface and its biological history. One of the most famous and well-preserved examples is the Barringer crater in Arizona, a relatively young impact structure formed approximately 50,000 years ago by an iron meteorite about 50 meters across. This crater, nearly a mile wide and 550 feet deep, provides a stark visual reminder of the destructive power of even a relatively small cosmic projectile, demonstrating the catastrophic potential of space rocks. Another notable example is the Sudbury Basin in Ontario, Canada, one of the oldest and largest confirmed impact structures on Earth, dating back about 1.8 billion years. This enormous elliptical structure, roughly 60 kilometers wide and 30 kilometers long, is thought to have been created by a bolide estimated to be at least 10 to 15 kilometers in diameter. The impact had profound geological consequences, leading to significant ore deposits of nickel, copper, and platinum group metals, making the region a world-renowned mining district. The sheer scale of the Sudbury event underscores the colossal forces unleashed during such ancient collisions, profoundly altering the Earth's crust. The Vredefort Dome in South Africa holds the record as the largest verified impact structure on Earth, with a diameter estimated to be between 250 and 300 kilometers. Formed about 2.02 billion years ago, the original impactor is believed to have been an asteroid up to 15 kilometers in diameter. While the original crater has largely eroded, the central uplift of the structure, known as the Vredefort Dome, is still visible. This ancient impact is another prime example of how extraterrestrial events can significantly reshape planetary geology, leaving behind vast, long-lasting geological features that continue to be studied by scientists seeking to understand Earth's deep past. Beyond these well-known terrestrial craters, evidence of ancient impacts can also be found in geological strata and fossil records. Tektites, small glassy objects formed from terrestrial debris ejected during large impacts, have been found in various locations, indicating significant ancient events. The presence of shocked quartz, a mineral altered by intense pressure from impact, and elevated levels of iridium, an element rare in Earth's crust but common in asteroids, provide further geochemical fingerprints of these cosmic encounters. These subtle clues allow scientists to reconstruct impact events even when no visible crater remains, painting a more complete picture of our planet's bombardment history. These famous impacts serve as powerful reminders that Earth is not immune to cosmic visitors. They illustrate the diverse scales and consequences of such events, from localized devastation to continent-sized geological alterations. Studying these historical impact sites helps scientists understand the mechanics of crater formation, the long-term environmental effects of large impacts, and the frequency of such events throughout geological time. This knowledge is crucial for assessing modern-day impact risks and developing strategies for planetary defense, ensuring we learn from the past to protect our future. Part 4. The Dinosaurs' Fiery End. Perhaps the most famous and unequivocally catastrophic impact event in Earth's history is the one widely believed to have caused the extinction of the non-avian dinosaurs approximately 66 million years ago. This cataclysmic event, known as the Cretaceous-Paleogene or KPG extinction event, marked a profound turning point in Earth's biological narrative, paving the way for the rise of mammals and ultimately humans. The primary evidence for this massive impact comes from a thin layer of iridium-rich clay found globally at the KPG boundary, a geological signature of an extraterrestrial object, as iridium is rare on Earth's surface but common in asteroids and comets. The impactor, estimated to be about 10 to 15 kilometers in diameter, struck the Yucatan Peninsula in what is now Mexico, creating the massive Chicxulub crater. This submerged crater, roughly 180 kilometers in diameter, was discovered through geophysical surveys and subsequently confirmed by drilling. The sheer energy released upon impact was equivalent to billions of atomic bombs, triggering a cascade of devastating environmental effects that rapidly transformed the planet's climate and ecosystems. The immediate aftermath was unimaginably violent, far exceeding any natural disaster experienced in recorded human history. The impact generated enormous tsunamis that scoured coastlines thousands of kilometers away, leaving behind distinctive geological deposits. A vast plume of superheated material, dust, and sulfur aerosols was ejected into the atmosphere, blocking out the sun for months or even years. This impact winter halted photosynthesis, leading to the collapse of food chains across the globe. Plants died, herbivores starved, and subsequently carnivores perished. The sudden and prolonged darkness, coupled with a dramatic drop in global temperatures, created an uninhabitable environment for many large, specialized creatures, including the dinosaurs. Beyond the initial darkness and cold, the impact also triggered widespread wildfires, fueled by ejected debris raining back down to Earth. The ignition of vast forests would have released immense amounts of soot into the atmosphere, further exacerbating the darkness and contributing to respiratory issues for surviving animals. The vaporization of sulfur-rich rocks at the impact site also released enormous quantities of sulfur dioxide into the atmosphere, which would have reacted with water vapor to form sulfuric acid aerosols, leading to widespread acid rain that further devastated terrestrial and marine ecosystems. This toxic deluge compounded the environmental catastrophe. The KPG event stands as a stark reminder of Earth's vulnerability to cosmic bombardment and the profound influence such events can have on the course of evolution. While the dinosaurs were wiped out, some forms of life, particularly smaller, adaptable creatures and those able to survive in freshwater or underground environments, persevered. The niches left vacant by the dinosaurs allowed for the diversification and proliferation of mammals, setting the stage for the emergence of modern life. This extinction event dramatically illustrates that life on Earth is not solely shaped by internal geological forces, but is also profoundly influenced by external cosmic phenomena, serving as a powerful lesson in planetary vulnerability. Part 5. Modern near-Earth objects and threats. In the vast cosmic ocean, Earth is constantly navigating a swarm of celestial debris, some of which poses a potential threat. Near-Earth objects, or NEOs, are asteroids and comets whose orbits bring them within approximately 1.3 astronomical units of the Sun, meaning they can get relatively close to Earth's orbit. While the vast majority of these objects pose no immediate danger, astronomers are diligently working to identify, track, and characterize them, creating a comprehensive inventory of potential impactors. The goal is to detect any hazardous objects far enough in advance to potentially implement mitigation strategies, ensuring that we are not caught off guard by a dinosaur-killing type event. The primary threat from NEOs comes from asteroids, as comets on Earth-crossing orbits are generally less common and often have highly eccentric paths that make them harder to predict with long lead times. Most asteroids are found and tracked through dedicated surveys that repeatedly scan the sky, looking for moving objects against the background of stars. Telescopes like those used by NASA's Planetary Defense Coordination Office, and international collaborations like the International Asteroid Warning Network, systematically observe the night sky, compiling vast databases of orbital information. This continuous monitoring allows scientists to calculate the probability of future close approaches and potential impacts, classifying objects based on their risk level. While a catastrophic impact like the KPG event is extremely rare, occurring perhaps once every tens to hundreds of millions of years, smaller impacts are more frequent. Objects a few tens of meters in size, capable of localized but significant damage, impact Earth roughly every few centuries to millennia. For example, the Chelyabinsk event in 2013, where a meteoroid about 20 meters in diameter exploded over Russia, demonstrated the potential for even relatively small objects to cause significant airbursts, generate shock waves that shatter windows, and injure people. Such events highlight the need for robust detection and warning systems, even for objects not large enough to cause global devastation. The challenge lies in detecting the smaller yet still dangerous NEOs. While large asteroids are relatively bright and easier to spot, objects less than a few hundred meters in size can be difficult to detect until they are relatively close to Earth. Current efforts are focused on improving detection capabilities and refining orbital predictions for known NEOs. This involves upgrading telescopes, developing new observation techniques, and fostering international cooperation to share data and expertise. The more lead time we have for a potential impactor, the more options become available for preventing a collision, ranging from evacuation plans to active deflection missions. The continuous monitoring of NEOs is an ongoing testament to humanity's growing awareness of its cosmic environment and its proactive approach to planetary safety. It represents a fundamental shift from passively observing the skies to actively protecting our planet. While the probability of a major impact in our lifetimes remains low, the potential consequences are so severe that the investment in planetary defense is considered a crucial endeavor. The goal is not just to track known objects, but to discover the vast majority of as yet undiscovered NEOs, particularly those in the size range that could cause regional devastation, turning the unknown into the known. Part 6. Comets as Messengers of Water and Life. Beyond their potential as destructive impactors, comets are increasingly viewed as celestial messengers, potentially delivering some of the fundamental ingredients for life to early Earth. The dirty snowball composition of comets, rich in water ice and various organic molecules, makes them prime candidates for having contributed to Earth's early oceans, and perhaps even the genesis of life itself. In the turbulent early solar system, when Earth was a molten world, it is believed to have been too hot to retain significant amounts of water during its formation. This suggests that a substantial portion of Earth's water must have arrived later, potentially delivered by comets and asteroids. Evidence supporting the cometary delivery of water comes from studying the isotopic signature of water in comets. Water molecules, H2O, can contain different isotopes of hydrogen, specifically deuterium, a heavier isotope. The ratio of deuterium to hydrogen, D/H ratio, in Earth's oceans is a key marker. Measurements from several comets, particularly those from the Jupiter family, have shown D/H ratios that are somewhat higher than Earth's ocean water, suggesting that while comets were contributors, they might not have been the sole source. However, comets from the Oort cloud, pristine relics from the solar system's birth, exhibit a wider range of D/H ratios, with some matching Earth's, indicating their potential role. Furthermore, comets are not just delivery vehicles for water, they are also cosmic repositories of complex organic molecules. These molecules, the carbon-based building blocks of life, have been detected in cometary dust and gas, including amino acids, which are the fundamental components of proteins. While these are not living organisms, their presence on comets demonstrates that the raw materials for life existed in the early solar system and could have been transported to planetary surfaces. The gentle delivery of these molecules through cometary impacts or atmospheric deposition could have provided the chemical precursors necessary for abiogenesis on early Earth. The Rosetta mission to Comet 67P/Churyumov-Gerasimenko provided unprecedented insights into cometary composition, confirming the presence of a wide array of organic compounds, including those never before detected in comets. The lander Philae, despite its challenging landing, gathered crucial data on the comet's surface, showing a mix of ice and dust, and reinforcing the idea that comets are veritable chemical factories, preserving primordial compounds. These findings have significantly strengthened the hypothesis that comets played a vital role in Earth's chemical evolution, potentially seeding our planet with the very foundations of biological complexity. The exploration of comets thus transcends merely understanding their physical properties. It delves into the profound questions of our origins. By studying these icy time capsules, scientists are piecing together the narrative of how Earth became a habitable world, capable of supporting the rich diversity of life we see today. The notion that the water in our oceans and the carbon in our bodies might have once traveled across vast cosmic distances, locked within the frozen hearts of comets, adds a poetic and profound dimension to our understanding of the universe's interconnectedness and the accidental ballet of creation. Part 7. Missions to chase comets and land on asteroids. Humanity's curiosity about asteroids and comets extends far beyond passive observation. It has propelled us to undertake ambitious space missions to chase these cosmic wanderers, even landing robotic probes on their surfaces. These missions are not merely technological feats, but scientific expeditions designed to unlock the secrets held within these primordial objects, providing direct measurements and samples that cannot be obtained through telescopic observations alone. The data gathered from these close encounters is invaluable for understanding the early solar system, the origins of water and life, and the potential for utilizing space resources. One of the most iconic comet-chasing missions was ESA's Rosetta, which orbited Comet 67P/Churyumov-Gerasimenko for over 2 years, from 2014 to 2016. Its Philae lander made history by achieving the first-ever soft landing on a comet's nucleus, albeit a challenging one. Rosetta meticulously studied the comet's nucleus, coma, and tail, providing a wealth of data on its composition, activity, and internal structure. The mission revealed the presence of complex organic molecules, detected water with a deuterium to hydrogen ratio different from Earth's oceans, and observed geological features on the comet's surface, fundamentally transforming our understanding of these icy bodies. Asteroid missions have been equally groundbreaking. NASA's Near Shoemaker became the first spacecraft to land on an asteroid, Eros, in 2001, after orbiting and mapping its surface for a year. More recently, Japan's Hayabusa and Hayabusa 2 missions successfully collected samples from asteroids Itokawa and Ryugu, respectively, and returned them to Earth. These tiny, pristine samples, measured in milligrams, offer a direct look at the unaltered material from the early solar system, revealing details about asteroid composition, mineralogy, and the processes that shaped them. The analysis of these samples continues to provide revolutionary insights into planet formation. NASA's OSIRIS-REx mission is another pioneering effort, having successfully collected a significant sample from asteroid Bennu in 2020. The spacecraft is currently on its way back to Earth, scheduled to deliver the precious sample in 2023. Bennu, a carbonaceous asteroid, is believed to be rich in organic molecules and water-bearing minerals, offering clues about the delivery of these essential ingredients to early Earth. The intricate maneuver of touching down on the asteroid's rugged surface to collect the sample demonstrated remarkable engineering prowess and meticulous planning, highlighting the complexities of such deep space operations. These missions are at the forefront of planetary science, pushing the boundaries of technology and human ingenuity. They represent a global effort to explore and understand our cosmic neighborhood, not just for scientific curiosity, but also for practical applications like planetary defense and resource utilization. The data and experiences gained from these pioneering endeavors are crucial for planning future missions, whether they involve sending humans to asteroids or developing strategies to divert a potentially hazardous object. The ability to directly interact with these celestial bodies marks a new era in space exploration, moving beyond distant observations to tangible, in situ investigations. Part 8. Mining Dreams and Space Resources. The vast abundance of raw materials in asteroids and comets has ignited visions of space mining, transforming these cosmic rocks from potential threats into valuable resources for humanity's expansion into the solar system. The concept is simple yet revolutionary. Instead of launching everything from Earth's deep gravity well, Future space endeavors could rely on materials extracted directly from asteroids, making space exploration and settlement more sustainable and economically viable. This stream of celestial resource extraction is moving from the realm of science fiction to serious scientific and engineering consideration, with significant implications for our future in space. Asteroids are rich in a variety of valuable materials. Many are metallic, containing iron, nickel, cobalt, and platinum group metals like platinum and palladium, which are scarce on Earth but crucial for modern technology. Other asteroids, particularly the carbonaceous chondrites, contain significant amounts of water-bearing minerals, as well as carbon compounds. Water, in particular, is an incredibly valuable resource in space. It can be used for drinking and life support, but more importantly, it can be split into hydrogen and oxygen, which serve as rocket propellant. This in situ resource utilization, or ISRU, would enable spacecraft to refuel in orbit or at lunar outposts, dramatically reducing the cost and complexity of deep space missions. The economic potential of asteroid mining is staggering. Estimates suggest that a single medium-sized metallic asteroid could contain more platinum group metals than have ever been mined on Earth, potentially worth trillions of dollars. While the initial investment in developing asteroid mining technology would be substantial, the long-term benefits could be transformative, creating entirely new industries and economies in space. Access to these resources could also alleviate some of the environmental pressures associated with terrestrial mining, offering a more sustainable pathway for meeting humanity's growing demand for essential elements. However, significant technological and logistical challenges remain. Developing the robotics, processing equipment, and infrastructure required to extract and refine materials in the vacuum and microgravity of space is a monumental undertaking. Transporting these materials to Earth or to other space destinations would also require efficient and cost-effective propulsion systems. Furthermore, legal frameworks and international agreements for owning and exploiting extraterrestrial resources are still nascent, requiring careful consideration to avoid potential conflicts in the future. The sheer scale of the endeavor demands a collaborative and international approach. Despite these hurdles, the allure of space resources continues to drive innovation and investment. Several private companies and national space agencies are actively researching and developing technologies for asteroid prospecting and resource extraction. The long-term vision includes establishing fuel depots in Earth orbit or at lunar Lagrangian points, powered by asteroid-derived propellant, and potentially even constructing habitats and manufacturing facilities using extraterrestrial materials. The dream of mining asteroids represents not just a quest for wealth, but a bold step towards expanding humanity's footprint beyond Earth, making us a truly multi-planetary species. Part 9. Planetary Defense and Asteroid Redirection. The understanding that asteroids and comets pose a genuine threat to Earth has led to the development of, quote, planetary defense, a concerted effort to detect, track, and, if necessary, mitigate the risk of impacts. This scientific and engineering discipline is a testament to humanity's growing capacity to proactively protect itself from cosmic hazards, moving beyond simply observing the skies to actively safeguarding our planet. The ultimate goal is to prevent a catastrophic impact event, like the one that ended the reign of the dinosaurs, ensuring the long-term survival and flourishing of life on Earth. The cornerstone of planetary defense is comprehensive asteroid and comet detection and tracking. Global networks of telescopes, both ground-based and space-based, continuously scan the sky, identifying near-Earth objects or NEOs, and meticulously calculating their orbits. Organizations like NASA's Planetary Defense Coordination Office and the International Asteroid Warning Network, IAWN, coordinate these efforts, sharing data and expertise across international borders. The aim is to achieve a sufficient warning time for any potentially hazardous object, ideally years or decades, to allow for effective mitigation strategies to be developed and implemented. Should a dangerous object be identified on a collision course with Earth, several deflection strategies are being investigated, categorized primarily into kinetic impactors and gravity tractors. A kinetic impactor involves intentionally crashing a spacecraft into the asteroid to alter its velocity and subtly change its orbital path. The DART mission, a collaborative project between NASA and ESA, successfully demonstrated this technique by impacting asteroid Dimorphos in 2022, proving that such a method is viable. Even a small change in velocity, applied far enough in advance, can cause the asteroid to miss Earth entirely. The gravity tractor concept involves stationing a heavy spacecraft near the hazardous asteroid. The subtle gravitational pull between the spacecraft and the asteroid, over an extended period, would gradually tug the asteroid off course. This method offers a more gentle and precise way to deflect an asteroid, especially for objects that are loosely aggregated, or rubble piles, where a kinetic impactor might cause fragmentation rather than a clean deflection. While still in conceptual stages, the gravity tractor represents a sophisticated and non-destructive approach to planetary defense, offering precision without directly touching the asteroid. Beyond these active deflection methods, other concepts include using lasers to ablate material from the asteroid's surface, creating a tiny thrust that nudges it off course, or even nuclear explosions in space. The latter, however, carries significant risks of fragmentation and radioactive contamination, making it a last resort. Planetary defense is a long-term endeavor, requiring continuous investment in research, technology development, and international cooperation. It is a proactive and forward-thinking strategy, demonstrating humanity's commitment to ensuring a safe future for our planet, a collaborative shield against the unpredictable forces of the cosmos. Part 10. How Impacts Shaped Human Imagination. From ancient myths of dragons and thunderbolts to modern science fiction blockbusters, the idea of cosmic impacts has profoundly shaped human imagination, leaving an indelible mark on our storytelling, fears, and aspirations. Long before scientific understanding could explain their true nature, meteorites and comets were often seen as omens from the gods, harbingers of doom, or divine messages, reflecting humanity's primal awe and terror in the face of unpredictable celestial phenomena. The fleeting appearance of a bright comet or the fiery streak of a meteor would undoubtedly have been interpreted as supernatural events, embedded deeply into cultural narratives. Many ancient cultures viewed comets with a mixture of fear and fascination. Their dramatic appearance, often accompanied by a luminous tail, was frequently interpreted as a bad omen, foretelling wars, famines, or the death of kings. For example, Halley's Comet has been recorded throughout history, with its appearance often associated with significant historical events, as if the cosmos itself was signaling terrestrial happenings. This deep-seated fear of comets as bringers of misfortune speaks to a time when celestial events were entirely beyond human comprehension, making them fertile ground for myth-making and superstitious beliefs, shaping the fabric of early civilizations. The discovery of impact craters on Earth, and later on the Moon and other celestial bodies, fundamentally shifted our understanding of our place in the universe. It moved the concept of cosmic collisions from the realm of myth to scientific fact, sparking both scientific curiosity and a renewed sense of vulnerability. This scientific awakening gave rise to a new genre of fiction, where asteroids and comets became the ultimate antagonists, threatening humanity's existence. Films like Armageddon and Deep Impact captured the public's imagination, exploring scenarios of global catastrophe and heroic efforts to avert disaster, reflecting a modern anxiety about external threats. These fictional portrayals, while often embellished for dramatic effect, have played a crucial role in raising public awareness about the real threat of asteroid impacts. They have fostered a societal understanding, albeit sometimes sensationalized, that Earth is not isolated, but part of a dynamic and sometimes dangerous cosmic environment. This cultural impact has arguably contributed to the public and political support for planetary defense initiatives, transforming a niche scientific concern into a recognized global imperative. The imagination has thus served as a powerful catalyst for scientific and technological advancement, converting fear into proactive measures. Ultimately, cosmic impacts continue to inspire both fear and wonder, reminding us of our fragile existence in the vastness of space. They are a potent reminder of the raw power of the universe and the constant interplay between cosmic forces and life on Earth. From ancient myths to modern scientific endeavors, the specter of falling stars and icy wanderers has consistently fueled human creativity, driving us to understand our place in the cosmos, to predict its dangers, and to dream of a future where we can not only survive, but thrive in an unpredictable universe. This interplay between imagination and scientific reality continues to shape our perception of the cosmos.